Hi, this video is going to be on stepper motors. As you've probably been watching my channel lately, you've seen that I've been doing lots of 3D printing projects. Lately I've been doing some gear related, some mechanism type projects, and I thought it'd be fun to motorize those projects. So I decided to go with stepper. So why did I choose stepper motors as opposed to some other choice like a gear motor or a low power DC motor? Well, the stepper motor, it seems to me it has three advantages. One, it's got pretty good torque. You can turn a lot of force with it, which is good for some of my 3D printed projects because when I start putting lots of 3D printed gears together, you do end up with some load torque to be able to turn it. Another advantage, it seems to be pretty good for its size. You can get these sort of flat pancake style steppers, not very thick, whereas a gear motor can get kind of long. A third advantage is they have pretty good holding power. If you've got something where you want to position a load and then you want it held there, the stepper, since its coils will be energized, will hold it in place. And the fourth advantage is that they're pretty precise. If you look at CNC machines or you look at 3D printers, they're using stepper motors. So I decided to experiment with some of these. I think this is probably my first stepper motor related project. I've done some other projects with just normal DC motors before, but I don't think I've done a stepper project. And here you're seeing a couple of completed projects, which I'll get into in a moment. Hi, this here is a NEMA 17 stepper that just showed up from Amazon. Out of here, it's a short body stepper. So stepper motors typically driven by 4 wires. This one has a green, blue, black, and red. So this shows that black and green are one pair, red and blue are the other pair. It has an order here to pulse the wires to make it go clockwise or counterclockwise. Simple enough. So what you're seeing here is a blog post up on DigiKey's website. DigiKey has this really awesome blog post that explains the stepper motors and how they work and how to drive them. So I printed it out. Here it is. And it's really pretty simple. There's 2 coils in the stepper motor, the A coil and the B coil. This is for a bipolar stepper. And you need to be able to apply currents in various directions on these. You've got the A coil and the B coil. You drive the A in one direction, then you drive the B in one direction, then you drive the A in the reverse, and then you drive the B in the reverse, and that will comprise a step. And then you just sort of repeat that indefinitely. There should be about 200 steps per revolution on the typical 1.8 degree stepper motor. You can get 0.9 degree stepper motors that will have more steps per revolution. So how do we drive these coils in these stepper motors? The typical thing that people use is something called an H-bridge. H-bridge in this example has 4 transistors, and if you drive this pair of transistors, the current flows that direction. If you drive this pair of transistors, the current will flow in the reverse direction. Simple enough. As the page points out, don't drive this pair of transistors or the current will flow through the transistors rather than through the motor and would burn up your H-bridge in a hurry. So certainly you can buy H-bridge driver chips. So here's an example of an H-bridge driver chip that I've used in some of my other projects to drive simple DC motors, and it's capable of running the direction of the motor forward or reverse. You could use that same chip for a stepper motor if you wanted to, but there is a much better way. So rather than use the H-bridge directly, you can buy yourself a stepper motor driver that includes the H-bridge and some other circuit like current limiting circuit and step and direction logic and other stuff like that, even micro-stepping support. So what I did, I bought like 5 of these A4988 drivers on eBay. It's like 5 of them were like $8 or something, very cheap. Only to realize as soon as I got them that these had an 8-volt minimum power. And my whole goal with this project I was designing was to run the project off of 5 volts so I could power it from a typical USB power bank. So this A4988 that was very cheap and easily sourced and that I had 5 of was not useful to me. So what I did, I looked online and I found some other companies that make stepper drivers. So Pololu is a company that has all kinds of options, and I bought their DRV8834 board. So the advantage of the DRV8834 is that it operates on a much lower power range than that A4988 style. The disadvantage is I have to buy them from Pololu, and they cost like $6 each. So they're quite a bit pricier to get these from the reputable name brand manufacturer than to get those no-name A4988 clones off of eBay. So I ponied up the money, I got some of these. So you can see on here, it does have a very tiny surface mount component that is the driver chip. You can actually get that in a slightly larger package, and I've been tempted to get some of them and design some of my own integrated boards. I haven't got around to that yet. These driver boards from Pololu are pretty darn convenient. There's also a little tiny potentiometer here that lets you set the current limit, and there's a wealth of bypass capacitors and pull-up, pull-down resistors, things to get the various logic operating correctly. So if you look at the online instructions for this, you'll see that it has a step and a direction, and it has a sleep pin. The sleep pin will put the driver to sleep. It stops outputting current. The step in the direction, the direction either high or low will control which direction it goes, and one step pulse on the step pin will make the motor step one step. Easy enough to interface too. Plugs right here into my board. So let's talk about micro stepping really quickly. So as I said at the beginning of the video, the stepper motor, these typical 1.8 degrees per step. You can buy other ones that are 0.9 degrees per step. But people have realized that there are ways to get fractions of steps. So the first thing is a half step. And a half step would, I think it's like by energizing both the coils at the same time, something like that, you're able to kind of position it halfway between the two step positions. But then there's also micro-stepping, which is even more fractional than that. And that has to do with putting different currents on the two coils. So that one coil is energized more than the other, and you'll get some fraction of a half step. So why would you actually want to do that? Well, one reason to do that is to get additional precision out of your stepper. But the other reason has to do with something, there's a self-resonating frequency in this thing. So I've already got this thing all soldered up, so I don't really want to change the micro-stepping and demonstrate it, but operating at full stepping mode with this motor, if I let it free spin and get around 100 hertz, it'd just kind of sit there and bounce. Because I think the acceleration of the step was so great that it was, partially skipping and then skipping back. I'm not sure, but looking online, you see other people complaining about this. So the good thing is, once I enabled micro-stepping on the driver, that problem completely went away. There was none of that weird resonating thing at 100 hertz. Thing accelerated smoothly through every stepping rate I tried to give it. So let's talk about current limiting for a second. So this here, I believe, was a 3.3 volt motor. I'm going to supply it with 5 volts. That would be too much. That would be too much current in the coils. So the current limiting feature via the potentiometer is really handy for that. We can have a higher voltage, and it will limit the current down to what's safe for the motor. And the claim is also that you can achieve higher stepper rates by using the higher voltage with a current limit rather than using a fixed voltage. So it seems a pretty good win to have the current limiting feature in this driver. So my first motivating project is Laius Gear Toy. So this is a toy that I printed up for my daughter. I found the original on Thingiverse. Here's a link to the original Thingiverse. I modified several of the gears myself to make some special ones like this swirly gear, and spoked gears, and lettered gears, the dragonfly gear, stuff like that. All of these have bearings in them, so you can see the little white bearing inside of here, skateboard bearings, and a magnet on the back that holds it to a refrigerator, or in my case, a Costco whiteboard. I've added triple bases for the bigger gears, and you can turn it all with the crank. Also added this planetary gear setup here. It's your typical planetary fidget spinner, but mounted to the base and made so it'll engage the rest of the gears. So my thought was I will take and I will run this with a stepper motor. So let's take a look at the circuits that I came up with for my project. So the first thing I wanted to do was just a simple potentiometer based speed control. You set the potentiometer one side, it goes very slow. You set the potentiometer the other side, it goes very fast. Now what occurred to me, first off, is I could use a 555 timer for this project, but I didn't actually have any 555 timers sitting around. And it's also, this day and age, it's a little bit of a pain to do a 555 timer because you've got to get the right capacitor, the right resistors. If you decide you want to change your frequency, you might actually have to change some components. So I decided, why not try to do this with a microcontroller? So what I've got here is an AT Tiny 85. So I've used the AT Tiny 85 in several of my other projects. It's a great little microcontroller that it has a bunch of analog inputs, perfect for a potentiometer. It's a small, it's like an 8-pin dip package, requires no external crystal. So I put together this relatively simple board here that has the Pololu 8834 driver and has the AT Tiny 85. I wired all three of the control lines from the Pololu, the sleep, the step, and the direction to the AT Tiny 85. And I also hooked a potentiometer to one of the ADC inputs. You actually see two potentiometer footprints there, because I wanted to be able to place a potentiometer in two different orientations. I reserved two other buttons for the remaining two pins. I could use one of them as a reversing button and maybe one of them as a power on-off toggle. I haven't got around to implementing those yet. I put a power jack in, I put a header to connect the motor. I put a header here to supply power to the motor, so I can supply it either off the 5 volts that runs the microcontroller, or I could wire in an external voltage for the motor. Got some pads over here for configuring the motor configuration bits, the enable bit, the config bit on the driver. For my simple project, I was able to leave all of those unpopulated, just go with the default settings. Then over here is a jumper that allows me to get the voltage reference out. So the voltage reference from this VREF pin on the Pololu board can be used to tell you what the current limit is. The current limit is, I think, twice the voltage reference. So if you get just your potentiometer, so it's saying 0.3 volts on this pin, then you will be getting 0.6 amps of current. So that's nice to be able to set the current limit before you hook up a motor. And then finally there is a relatively beefy 100 microfarad capacitor. The Pololu datasheet says put that in because there will be some voltage transients and spikes and stuff due to driving the motor, and you don't want that frying logic. Okay, I've got my USB power pack. Let me plug it in, turn the speed down. So it's actually running very slowly right now. I can feel it. As you turn it up. So it does make some noise at various frequencies. Kind of hear it kind of humming. Definitely feel a vibration in the frame. You can make it go really slow. Down at the super slow rates, like it's slower than that. It starts to get a little bit intermediate just because I think it's picking up noise on this potentiometer. Like right there. Kind of getting tick, 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 tick. Kind of when you put the potentiometer really low like that. So as far as attaching this to a gear, there are magnets on the underside of this. So here's a picture of the rotor. There's 3 pockets for magnets. The rotor pushes on. Then the matching gear up here has 3 magnets as well. So you put this on there and it holds it securely. It's kind of a magnetic clutch. So since I'm going to be letting my daughter play with this, I wanted it to be safe so that if anything bad happens, the gear will slip. So there it is, free spinning. And if it's obscured, it just kind of skips like that. So here, going pretty fast. Still slipping. So I also decided to do a Raspberry Pi version in addition to the ATtiny85 version. The idea here is we'll be able to control it with a web browser, cell phone, that sort of thing. So we've got a Raspberry Pi Zero header, and we've got the Pololu driver. Again, the driver has a 4-pin header for the motor, a 100 UF capacitor to reduce transients and stuff on the motor power, a jumper to set the motor power, various pads to jump features to it. Then the sleep, step, and direction are wired to the Raspberry Pis GPIO 17, 18, and 27. Now I specifically chose to hook step up to pin GPIO 18 because that one does have hardware PWM capability. So my thought there is that rather than doing software pulse generation, we could use the Raspberry Pi's hardware pulse generation to generate the frequency to drive the stepper at a certain speed. Also have a couple buttons that I have not yet used, and instead of the potentiometer I went with an encoder. So this is a SparkFun encoder. It's an RGB encoder. It has red, green, and blue LEDs in it, as well as a push down switch and then the typical encoder lines. So that's just a matter of preference whether you go with a potentiometer or an encoder. The encoder is easier to wire to the Pi because the Pi doesn't have built-in analog to digital conversion. But it also gives you more precise control because an encoder is inherently a digital device, whereas a potentiometer can drift due to voltage spikes or heat or various other issues. I put in dropping resistors for the LEDs, and I put in current limiting resistors for the switches. I usually put those current limiters in just to cover the case of a programming error where one accidentally configured these pins as outputs instead of inputs. And they're just all wired to various pins over here on the Raspberry Pi. Here's the board I designed to go along with the Raspberry Pi. So there's a header coming out the back. It'll mate up to this header on the Pi, 0W like so. They'll be clamped together inside a case. Pull them back apart, we'll look at it. So here is a small 3.5 by 1.3 millimeter 5 volt power jack, 10 UF capacitor, the Pololu driver board, RGB encoder. You can buy those at SparkFun. Some dropping resistors for the encoder, some optional push buttons I'm not going to use, and a decoupling capacitor and a header to get the reference voltage out of it. Simple enough. Let's put it in a case. So since we do have the push button capability, I have made it so it defaults to not powered up. So when it's in sleep mode, you can freely turn the motor because there's no power going to the coil. As soon as I push this button, it will go into running mode. Whoops, need a little bit of debounce. There we go. And I've made this so it should flash between green and red at approximately once per revolution. So we should be able to slow it down. I mean, right now it's going really slow. And just as before, we can plop the gear on there if we want, and it'll slip. There was a slip. So I can slow it down to a complete crawl here. Now we're getting a tick every second or so. Spinning it up. Got it going pretty fast at this point. So we can also run it from my cell phone because of the Raspberry Pi Wi-Fi interface. So turn it on, turn it off, adjust the frequency. Okay, finally, let's try it out on Laius Gear Toy. So I've positioned it here next to this green gear. All the other gears are engaged. It should work. There it goes. So it's not the smoothest motion. I think maybe because there is some friction in all of these gears. It's going a little better now. I think it is maybe slipping here slightly on the clutch every so often. Yeah, there was a clutch slip. We turn it up. Run a little bit better at higher speeds. If there's an accident, you'd start skipping just like we wanted. So let's see how fast we can make it go. Must be about full speed. Here is helical cage gear cups with a stepper motor drive. So the stepper motor drive is based on a Pololu DRV8834 together with a Raspberry Pi Zero-W and an encoder. If we push this, it'll start. It's running at a very slow speed. Crank the speed up. It's going quite fast now. Full speed. That's probably about as fast as you want that thing to go. And I do plan on making the center cup taller. This kind of half height one was just my first attempt at the center cup with the rotor for the stepper motor. So we could certainly could put, well, if I can get it on straight, certainly could be a taller one. Will work just fine like that. But I'll probably print one the same height as the other ones. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.